Hello everyone, I am pleased to present our CVPR 2026 main conference paper titled When Transformers Meet Mamba, a hybrid transformer-member network for video object detection. In this work, we propose Team-Member DET, a hybrid transformer-member framework for efficient and accurate video object detection. Existing transformer-based video object detection methods usually rely on spatial and temporal transformers to aggregate spatial-temporal information. Although transformers are powerful for long-range dependency modeling, their quadratic complexity makes temporal modeling expensive for long video sequences. To address this issue, we propose a hybrid design. Specifically, we use transformers for spatial modeling within each film, and introduce Mamba for efficient temporal modeling across films. Based on this idea, our main contributions include three key models: SADT for spatial feature enhancement, TCBM for temporal feature aggregation, and MAET for query feature interaction and alignment. This slide shows the overall framework of Team-Member DET. In a video sequence, each film is first processed by a shared backbone to extract token features, then positional encodings are added to the token features and fed into the spatial adaptive deformable transformer encoder, which enhances the intra-film spatial representations. Next, spatial encoder features from multiple films are concatenated and passed into the temporal cascaded bidirectional Mamba encoder, which efficiently models long-range temporal dependencies across films. Finally, the spatial temporal encoder features and object queries are fed into the Mamba entangled transformer decoder for query refinement, classification, and bounding box regression. This slide introduces the SADT encoder. The goal of SADT is to enhance spatial feature representations within each film. The input token features are first combined with positional encodings and then processed by multi-score adaptive deformable attention, different from standard deformable attention, which uses a fixed number of sampling points for all queries. SADT adaptively predicts the number of sampling points for each query. Specifically, a lightweight MLP predicts a sampling intensity score, which is mapped to a discrete number of sampling points. Therefore, simple features use fewer sampling points, while complex objects such as occluded or blurred objects are assigned more sampling points. In this way, SADT performs adaptive and object-aware spatial feature aggregation. This slide presents the TCBM encoder. Its input is the spatial encoder features generated by SADT, and its goal is to capture long-range temporal dependencies across video films. TCBM first uses a forward Mamba branch to model temporal dependencies in the forward direction. Then a backward Mamba branch is cascaded to capture temporal information in the reverse direction. By combining forward and backward temporal modeling, TCBM aggregates temporal information from both directions. The key advantage is that Mamba models long-range dependencies with linear complexity, making TCBM more efficient than temporal transformers for long video sequences. This slide shows the MAET decoder. Unlike SADT and TCBM, MAET focuses on refining object queries for final predictions. First, object queries are processed by multi-head self-attention to model co-recurring interactions. Then, multi-score adaptive deformable attention is used to build interactions between object queries and spatial temporal encoder features. After that, cascade bidirectional Mamba further captures long-range contextual information. In this way, MAET combines attention-based query feature interaction with Mamba-based contextual modeling, enable fine-grained query feature alignment. This slide compares Team-Member DET with state-of-the-art methods on ImageNet VID. With the ResNet 101 backbone, Team-Member DET achieves 87.9% MAP with only 20.6 ms inference time. With the stronger swing backbone, Team-Member DET further achieves 92.1% MAP, which is the best accuracy among all compared methods. The scatter plot also shows that Team-Member DET provides a strong trade-off between accuracy and efficiency. This slide reports results on applications 55, which contains more complex egocentric video scenes. With RosNet 101, T-Mamba data achieves 45.1% MAP, outperforming other RosNet 101-based methods. With SwimB, T-Mamba data reaches 50.8% MAP, again achieves the best performance. These results show that T-Mamba data generalizes well to more challenging video object detection scenarios. This slide presents the ablation studies. First, adding SADT, TCBM, and MAET consistently improves the baseline, and combining all components achieves the best result. Second, adaptive sampling in SADT provides a better accuracy efficiency trade-off than fixed sampling. Among different scan strategies, these results demonstrate the effectiveness of each key design in T-Mamba data. This slide shows the visualization comparison with TransView-D++ on ImageNet VID. The first row shows TransView-D++ and the second row shows T-Mamba data. We can observe that our method produces more robust detection results, detects more objects, and gives higher confidence scores. However, T-Mamba data still have limitations, as shown on the right. One extremely small score is missed. This indicates that extremely small object detection and complex motion remains challenging. This slide shows visualization results on applications 55. Although this dataset contains complex egocentric scenes and diverse objects, T-Mamba data still achieves reliable localization and correct classification. This further demonstrates the generalization ability of our method. To conclude, we propose T-Mamba data, a hybrid transformer Mamba framework for video object detection. SADT enhances the entry-film spatial feature representations, TCBM efficiently models long-range temporal dependencies, and MAET improves query-feature interaction and fine-grained alignment. Extensive experiments on ImageNet VID and Epic Kitchen 55 shows that T-Mamba data achieves state-of-the-art performance. Thank you very much for your time. This concludes my presentation.